Welcome to the Deep Dive. Today we're plunging into a really fascinating area. It's where cutting-edge manufacturing meets a pretty fundamental human need, bone repair.
Mm-hmm.
The sources you shared explore some, well, truly innovative ways to create custom bioceramic implants. They use a technique called Sintering-assisted additive manufacturing, or SAM.
Yeah, Sam. It's a bit of a mouthful, but the idea is powerful.
Think of it as like a new frontier in building bones, right?
Exactly, because, for too long, the standard methods for fixing bones or replacing joints, they've had their drawbacks.
Definitely.
Natural bone grafts, for instance, carry risks, rejection, contamination, and metal implants, while they've been crucial, let's be honest, they weren't really designed for the body.
Right, they're kind of foreign objects.
Precisely. And that can lead to problems down the line, like corrosion or even weakening the bone around them. That's called stress shielding.
Okay. And it's been a real puzzle, hasn't it? Trying to make complex ceramic parts, the kind that could potentially mesh perfectly with our own bone, but also making them strong enough, and of course, biocompatible.
Oh, that's been the core challenge.
But this is where it gets really interesting. This deep dive is all about how combining, the amazing design freedom of 3D printing with some pretty advanced heating techniques, sintering offers a genuinely promising way forward.
It really does.
We could be looking at personalized, high-performance, bioceramic bone scaffolds. So we're going to explore the different SAM approaches from these sources and really dig into what makes them work.
Sounds good. Let's maybe start with the materials themselves, bioceramics, things like hydroxyapatite, calcium phosphates.
Okay.
What's really amazing about these is how similar they are chemically to our own bone mineral.
Right, so the body recognizes them, sort of.
Pretty much, and because of that, they can integrate incredibly well with the existing bone. That process is called osseointegration.
Osseointegration, got it.
Think of it like the bone and the implant almost growing together, like roots finding soil.
That makes a lot of sense.
Yeah.
They're chemically familiar. And while metals, titanium alloys especially, they've been the workhorses for load-bearing stuff for ages.
True.
As the sources point out, they weren't really designed with our biology in mind, which can lead to those long-term issues we mentioned.
Exactly.
So bioceramics being more naturally compatible, they could be a much better long-term solution, potentially.
That's the hope. But, as you said, the big hurdle has always been manufacturing. How do you make these really complex, porous structures? Because bone isn't solid, right? It's got this network inside.
Yeah, that intricate structure.
How do you replicate that and make sure it's strong enough? Strong enough to handle walking, moving, all the stresses?
Right. Enter additive manufacturing, 3D printing.
Precisely.
This technology is it's revolutionary because it lets us build these complex 3D objects layer by precise layer. The design freedom is incredible.
Absolutely. Shapes, internal structures, things that were just impossible with traditional manufacturing are suddenly possible.
Yeah.
And the sources cover a range of AM techniques, material jetting, stereolithography, powder bed fusion, and so on. But there's a particular focus here on something called solvent jetting, or SJ.
Okay, SJ.
It's a type of powder bed inkjet 3D printing, sometimes called P3DP. The sources highlight it partly because it's relatively easy to use, and you get really fine control over the printing parameters.
Okay, so solvent jetting. How does that actually work? What's the mechanism? I gather it involves putting a liquid solvent on the powder.
That's the core idea. You have a bed of the bioceramic powder, and a print head moves across it, selectively depositing tiny droplets of a liquid solvent.
Like an inkjet printer, but with solvent.
Kind of like that, yeah. The solvent acts as a temporary binder, wetting the powder particles just where it lands, making them stick together. Layer by layer, you build up the shape.
And that initial shape is called the green body.
Exactly. The green body, it's the printed part, but it's not strong yet. It's fragile. It needs the next step. Oh, and it's worth mentioning indirect AM, too.
Right, indirect.
That's where you 3D print maybe a mold or a pattern, and then use that in a more traditional process to make the final part. We'll see that come up later.
Got it. So printing gives us the shape, the green body. But the sources really hammer home that the next step, sintering, is absolutely crucial.
Yeah.
Especially for ceramics.
Couldn't be more critical.
Okay, let's dig into that. What is sintering exactly, and why is it such a game changer here?
Sintering basically is heating that powdered material in the green body to a very high temperature. Importantly, it's below its actual melting point.
Okay, so not melting it.
No, not melting.
Yep.
The heat causes the surfaces of the individual powder particles to bond together. They fuse at the contact points, consolidating the whole thing into a solid, dense mass. That consolidation is what gives the ceramic its strength and durability. Without sintering, the green body would just crumble.
So it's like taking really fine sand and heating it just enough so the grains stick together really tightly, forming a solid rock.
That's a great analogy, yes. And just like there are different ways to print, there are different ways to sinter, conventional ovens, microwaves, and something called spark plasma sintering, SPS, which is pretty interesting.
Okay.
And another key thing, particle size matters a lot. Generally, smaller powder particles sinter better, more effectively, more quickly.
Why is that?
More surface area relative to their volume, so more points of contact between particles, which means bonding happens more readily.
Makes sense. More connection points. But the sources also stress for bioceramics, you have to be incredibly careful with the sintering. Why so critical?
It's about preserving the material's properties. You heat it too much or in the wrong atmosphere, and you could change the chemical composition of the bioceramic, or you could negatively affect its biocompatibility. The whole point is to keep it as close to natural bone mineral as possible so the body accepts it, right? So that osseointegration works properly.
Right. You need that perfect balance. Heated enough to make it strong, but not so much you ruin its bioproperties.
Exactly. It's a delicate process.
Okay, so now we get to the really core stuff.
Yeah.
The different SAM approaches your sources explored. Let's start with maybe the most direct one. Solvent jetting, then sintering. What do they find there?
Well, a really key thing was optimizing the printing parameters themselves. Things like how thick each layer is, the nozzle temperature. They have a huge impact on the density of that initial green body.
Okay.
And that green density directly affects the final strength and density after you sinter it. It's all connected. And what's really interesting is that the best layer height isn't just about the height itself. It depends on the powder particle size, too.
So it's not one size fits all. You have to tune it based on the powder.
Precisely. It's a balancing act. For instance, the research showed that using nano-sized alumina powder, granulated first, could lead to much higher final densities and strength compared to using larger micron-sized powders coated with a binder.
Nano-sized.
Yeah.
So incredibly tiny particles.
Very tiny. The idea is they pack together more efficiently in the green state and then form stronger bonds, stronger necks between particles during sintering.
That's fascinating.
Yeah.
Seems almost counterintuitive, working with such fine powder, but it pays off in the end product.
It seems so, but then you also have to watch the sintering time.
Ah, right. You mentioned that earlier. Too long is bad.
Yeah, you'd think longer is always better for density. But if you sinter for too long, the tiny crystal grains within the ceramic can start to grow too large.
And that weakens it.
Paradoxically, yes. Large grain growth can actually reduce the mechanical strength. So you need that sweet spot long enough for good density, but not so long that the grains get too big.
Tricky.
Definitely.
Yeah.
But another cool thing about solvent jetting is you can use it to design in macropores larger interconnected channels within the scaffold.
Which is crucial for bone, right? For cells and blood vessels.
Absolutely vital. Allows cells to get inside, blood vessels to form, and you can control the overall porosity level just by adjusting the printing parameters. It's like engineering the internal architecture.
Wow. So you can design that pore network
right
from the start. The sources also mention modeling, finite element modeling.
Right. FEMM. It's a computational tool. Basically, you build a virtual model of the printing and sintering process.
Okay.
It helps predict what the final density of the scaffold will be based on how it was printed. So you can optimize the printing settings digitally before you even make the part. Saves time, saves materials.
That makes perfect sense. Simulate, optimize, then build. Okay, so that's the direct approach. Now, the sources also talked about a different route. Indirect AM via subtractive sintering.
Yeah.
AMSS sounds complex.
It's actually quite clever, really ingenious, I think. Instead of printing the actual bioceramic part directly, you first 3D print a temporary mold, a sacrificial mold. The sources mention using things like maltodextrin, sugar, alumina mixed together.
You print the mold out of sugar and stuff.
Basically, yeah. This mold has the negative shape of the part you want. Then you fill that mold with your actual ceramic powder, say zirconia or hydroxyapatite.
Okay, fill the mold with the good stuff. Then what?
Then the whole thing, mold plus powder, goes into something called a cold isostatic press, CIP. CIP. Imagine squeezing it evenly from all directions with really high pressure. This packs the ceramic powder inside the mold incredibly densely, gets that green density way up.
Okay, high pressure packing.
Now, here's the really smart part. When you take this whole assembly and put it in the furnace for sintering, the sacrificial mold material is designed to swell up and crack apart in a controlled way as it heats up.
Wait, the mold breaks itself apart. On purpose.
Exactly. As it cracks and expands, it allows the high-density ceramic part inside it to shrink and consolidate properly during sintering without being constrained by the mold. And you don't need a separate step to burn out the ceramic binder because the powder was packed pure.
Wow, that is clever. The mold essentially self-destructs to free the part. So what's the advantage? What kind of parts does this AMSS work well for?
It seems particularly good for making components that are almost fully dense, which means very strong with complex external shapes. Think maybe dental crowns or small mechanical parts, maybe gears with simple internal channel.
High-density, complex outside shapes.
Right. You get potentially excellent mechanical properties. And again, modeling helps here too. Predicting how things deform during pressing and sintering lets you design the initial mold shape so the final ceramic part comes out exactly right.
Very neat. Okay, one more approach mentioned. Making powder parts with internal channels, using solvent jetting for the mold again, but this time with spark plasma sintering. SPS. How is this one different?
This one's really focused on creating those complex internal channels, like the blood vessel networks in bone scaffolds.
Ah, okay.
So you use solvent jetting again, but this time you print the mold out of graphite. The mold is the negative space of the channels you want inside the final part.
A graphite mold defining the internal voids.
Got it. Then you fill this graphite mold with your ceramic powder, like hydroxyapatite, or maybe even metal powder, like stainless steel.
And then, spark plasma sintering. What's special about SPS?
SPS is different from regular furnace heating. It applies high pressure, like CIP, but also passes pulses of strong electrical current directly through the powder and the graphite mold.
Pressure and electricity.
Yeah. This combination causes incredibly rapid heating and densification. You can consolidate the powder much faster and often at lower overall temperatures than conventional sintering. Big time saver.
Faster, lower temp. Sounds efficient.
Very efficient. And another big plus, the graphite mold itself means you don't need a separate debinding step for the ceramic or metal powder. That's often a tricky, time-consuming stage in other methods.
Right, the mold handles that. How do you get the graphite off afterwards?
It's actually pretty easy. You can usually remove most of it by sandblasting, and then a final heat treatment and air annealing burns off any tiny bits of residual carbon.
Okay, so SPS with a graphite mold gives you speed, efficiency, and helps with complex internal channels. What are the prime applications?
The sources really highlight making those advanced bone scaffolds with intricate, interconnected pore networks, mimicking natural bone vascularization.
Ooh, cool. For healing.
Absolutely.
Yeah.
But also potentially useful elsewhere. Think advanced heat exchangers, components for energy systems where you need complex fluid channels, and, no surprise, finite element modeling helps here too. Simulating the SPS process helps predict densification, potential warping, and optimize the graphite mold design.
It's really amazing seeing these different strategies all combining printing and sintering in unique ways to tackle these bioceramic challenges. Now, shifting gears just a bit, the sources also touched on market potential, customer discovery. What did they find there?
Yeah, that's super important, right? Does anyone actually want this stuff? The researchers did a lot of interviews, orthopedic surgeons, hospital managers, people in the medical device industry, and the feedback was overwhelmingly positive. A real sense of unmet demand, a clear clinical need for customizable bioceramic implants made with these kinds of technologies.
So, doctors see the benefit.
Definitely. They pointed to potential for better patient outcomes, fewer complications, and the huge appeal of personalized care. Those were the big drivers.
Okay. Is it seen as, like, financially viable, practical?
The research suggests yes, especially if new reimbursement pathways open up for innovative implants that show clear benefits. And importantly, it seems like these technologies might not require, massive changes to hospitals or surgical procedures. They could potentially fit into existing workflows.
That's key for adoption, isn't it?
Absolutely. Makes it much more likely to actually get used.
That's really encouraging. It's one thing to have cool science, but another for it to be practical and reach patients.
Exactly. That customer discovery piece is crucial validation. It confirms there's a real need and a potential path to market. That's how research turns into better healthcare.
So, as we wrap up this deep dive, what are the sort of main takeaways on SAM for bone repair?
I think the central message is that SAM combining solvent jetting, especially with smart sintering, whether that's direct free sintering of nanopowders or that clever AMSS indirect method with CIP, or using SPS with graphite molds, it really holds immense promise.
Yeah.
We're talking about creating complex, high-performance bioceramic implants and scaffolds in ways we couldn't before. Each method offers unique advantages, controlling porosity, getting super high density, making those intricate internal structures.
And for me, the real aha moment is just that shift away from standard, off-the-shelf implants, the potential for truly personalized solutions, using ceramics that mimic your specific bone, creating shapes with internal details needed for your healing. That feels like a huge leap for orthopedics.
No doubt. It's a move towards implants that aren't just passive replacements, but active integrated parts of the body.
It's been a really insightful look at the TAM. Really shows what happens when different fields, different technologies come together. So here's a final thought for you, the listener, to chew on. We've seen how combining advanced manufacturing and material science could revolutionize bone repair. What other really tough challenges, things that seem almost intractable now, could we maybe tackle by creatively mixing and matching technologies like this? Think about truly personalized medicine, tailored right down to the materials used in an implant designed just for you. It's a powerful thought. Thanks for joining us on this deep dive.